Hey everyone, let's take a look at the test 4 study guide. So 5.3 exponential functions. We will need to know that standard form of the exponential function, f of x equals c times a to the x. However, the periodic interest and continuous interest formulas will be provided to you. We need to be able to convert from a logarithmic form to exponential form. That's where if we have log base b of x equals y, then we can convert it to b to the y equals x, or other way around. We need to use the equivalence property of exponential expressions. That's where if we have two exponential functions with the same base, then the exponents are equal. And we'll see some examples of that, as well as how to find the domain of the logarithmic function. We need to be able to use the product, quotient, and power properties to combine or expand logarithms and know how to solve them. So let's take a look at our first problem. So we want to determine the final value of a $12,000 loan at 9% interest compounded quarterly for 3 years. So let's figure out what we've got first. We know our initial amount, our P, is 1,200. We have a rate of 9%, but we want to use that decimal representation or 0.09. It is in the account for 3 years, and it's compounded quarterly or 4 times a year. So we will use our periodic interest formula. We take our P times 1 plus R over N raised to the NT. When we plug that into a calculator, we get 1567.35. The next example, determine the final value of $500 invested at 6.5%, compounded continuously for 8 years. So again, let's see what we've got. We're starting with 500. We have an interest rate of 6.5%, and it's in the account for 8 years. So we want to use our continuous interest formula, that A equals P e to the RT. So our initial amount was 500 times e to the RT. And remember, when we use that e, when we're calculating this e, just use the e button on your calculator. And when we calculate that, we get 841.01. Now, suppose we decide to invest $2,000 as part of a retirement plan at a 6% interest rate, compounded monthly. How much will your account have in 20 years? So let's again look at what we've got. We've got an initial amount of 2,000. Our rate is 6%. It's in the account for 20 years, and it's compounded monthly or 12 times a year. Using our periodic interest formula, take our P times 1 plus R over N raised to the NT. So we get a value of 6,620. Oops. Sorry about that. 0.41. All right. What if instead we invested that same amount of money at 5.5%, being continuously compounded for 20 years? So we still have our same initial amount. Our rate is different this time, but it's still in the account for the same amount of time. So using our continuous interest formula, we have our initial amount times e to the RT. And that comes out to 6,008.33. So which one offers a higher return? We both started with the same amount, so whichever one ends higher has that higher return. So it's going to be option A. If one person initially knows the secret and shares it, then the number of people who know the secret's increasing by a factor of 2 for each hour x. So we want to write a exponential function that models a situation. So remember that our C is our initial amount. We had one initial person. Our A is whatever factor we're either growing or decaying by. So that's our C, that's our A. So that we can just write our function. Our C here is 1. See that our C is 1 and our A is 2. Since our C is 1, we'll just leave that out. We'll just write our A is 2 and leave it with the X. So now we have a exponential function that models the situation. So let's use the function to find the number of people who know the secret after 12 hours. So that means when X is 12, what is f of X? So, or in other words, what is f of 12? We just plug in 12 to our function that we just created, and we get a value of 4,096. All right, so we can find these exponential functions just using data as well. So remember that C is our initial amount, so it's wherever X equals 0. So this is our C right here. Our C is 1.5. And to figure out A, we need to use another set of the data. We need to use another ordered pair and plug that into our function. So we will have a function that starts off looking like f of x equals c times a to the x. And here we'll use x is 1 and our y or f of x equals 3. So we get 3 equals 1.5 a to the 1. A to the 1 is just a. So if we divide each side by 1.5, we get a equals 2. And that's everything we need for that exponential function. So our f of x equals c times a to the x. Suppose the table shows the number of subscribers for a YouTuber, where X is the number of months that have passed since they started posting content. So what is that exponential function that models this data? So again, we have that initial amount. We have C equals 480. So we've got some kind of initial function. It's going to be f of x equals 480 times a to the x. And we still need to figure out what is a. So we'll use another ordered pair, 2 and 1260. 2 is our x. X is the number of months. So that means our subscribers is 1260. So 1260 equals 480 times a squared. If we divide each side by 480, we're going to get a squared is 1260 over 480. We take the square root of each side, we get a is 1.62. All right, so we got our c, we've got our a, we've got our function. F of x equals c times a to the x. Now, let's evaluate and interpret f of 12. So f of 12, we'll take our function that we just created and input 12 for x. And when we do that, we get 162,780, rounding to the nearest whole number. So what does this mean? It means given an input of 12, we have an output of 162,780. So our input 12 is the number of months. So after 12 months, they had 162,780 subscribers. Next example. The Great Plague impacted a village located in England in 1666. The table shows the number of people who were infected after X days. Let's find an exponential function to model the data. Again, we look for that initial amount. We have at where our input X or days is 0, we have an output of 7. So our C is 7. So again, we'll kind of set up our initial formula, f of x equals 7a to the x. And we're going to use a different point to figure out what is our a. So our f of x here is going to be 21 times 7a to the 15th. If we divide each side by 7, we get a to the 15th equals 3. Now, there's two ways to do this. We can either take the 15th root of each side or raise each side to the 1 over 15th power. So if we have a to the 15th, raising that to the 1 over 15th, we'll get rid of those exponents. We'll just be left with a. But if we do it to the left side, we have to do it to the right side too. So we're left with a is 3 to the 1/15th power, or a is 1.08. So that gives us our function, f of x equals c times a to the x. And then let's evaluate and interpret f of 45. We'll just plug that in. We have 7 times 1.08 to the 45. And when we calculate that, we want to round to the nearest whole number, we get 223. So what does that mean? So for an input of 45, we have an output of 223. So that means after 45 days, 223 people were infected. Here we want to find what these logarithmic expressions are without using a calculator. So we want to basically set each of them equal to y, and we're going to use our equivalence property to evaluate it. So we set this equal to I. We're going to use that property. We have log base b of x equals y, then b to the y equals x. So here we have a base 4. So 4 to the y equals 1 over 16. So we need that right side to have a base of 4. We need to manipulate it in such a way. So the first step is to get that 16 up into the numerator. And one of those tricks that we learn is that we raise it to a -1 exponent that would be equivalent to that 1 over 16. Now, we're closer, but we still need a base of 4. Now, we know 16 is the same thing as 4 squared. So we can rewrite it as so, 4 squared. But we need to remember we still have that exponent of -1. So when we evaluate that right side, we get 4 to the -2. And now we have the same base. That equivalence property tells us that the exponents are equal. And we're done. We have y equals -2. Now, natural log of e to the 5th. So set that equal to y and convert to our exponential form. Natural log has a base of e. So that gives us e to the y equals e to the 5th. We already have the same base, so we can go ahead and use that equivalence relation. So we just say that y equals 5. And we're done. That was it for that one. Okay. Now, log base 3 of 9. Set that equal to y and convert to exponential. So 3 to the y equals 9. We can think of it two ways. We can just say, okay, we know it's 3 squared equals 9. So we can just go ahead and say y equals 2, or we can convert it to that different base. We know that 3 squared is 9, so we can rewrite it as 3y equals 3 squared. Now we have that same base, and we set the exponents equal to each other. And we've got y equals 2. And that's our final answer. Log base 5 of 1 over 25. Set it equal to y and convert to exponential. So that means 5 to the y equals 1 over 25. And we'll do similar to what we did in that first problem. Use that trick to get that 25 up into the numerator. And we need to get that same base. We need that 25 to have that base of 5 instead. We know that 25 is 5 squared. So we replace it with that. But don't forget that exponent. We simplify. We get 5 to the negative 2. And using the equivalence relation, we get y equals negative 2. Okay. Log base 2 of 32. Again, set it equal to y and convert. So 2 to the y equals 32. Here, you might need to play around with the calculator a little bit and figure out what power we might raise 2 to get 32. These problems on the test are going to be similar to this. There's not going to be anything crazy, you know. If we've got a 2 as a base on the left, we've got a 32 on the right, whatever that number is on the right, we should expect it to be able to easily get that same base as the left-hand side. So we can kind of assume that it's going to be 2 to some power. And here you might just need to play around with the calculator. 2 times 2 times 2 times 2 times 2 is 32, or 2 to the 5th. So now we have the same base. Equivalence property tells us that y equals 5. Right. And last one of these, natural log of e. This was one of the properties that we talked about in one of those sections. If we have, we know this is like a base e, right? We know that natural log has a little hidden base of e there. And so if we have the same base and the same argument, it's going to equal 1. But we can also do it the way we've been doing it before. We can set it equal to y and convert to exponential. We have that base e raised to the y equals e. We can think of e as e to the 1. And so y equals 1. Okay. Now, to find the domain of logarithmic functions, the argument has to be greater than 0. That is our restriction for the domain. So all you have to do is just take that argument, whatever's inside the parentheses, whatever's we're taking the logarithm of, and set it greater than 0. And then we'll solve for x. So if we add 5x to either side, we'll get negative 2 is greater than 5x. We divide each side by 5. We get negative 2/5 is greater than x. But, I like to have my x's on the left side. So I'm going to say x is less than negative 2/5. All right, so if we wanted to put that in interval notation, we want any value less than negative 2/5. So negative infinity to negative 2/5. Or that set builder notation, use the braces, say x such that x is less than negative 2/5. And then this one. We have t of x is natural log of 3x minus 1. It doesn't matter what base our logarithm is. Before, we had a base 5. Here, we have base e. It still works the same way. We still want to set our argument greater than 0. So We add 1 to either side. We get 3x is greater than 1. Divide each side by 3. X is greater than 1/3. So in interval notation, that domain would be from 1/3 to infinity. Or in set builder notation, x such that x is greater than 1/3. All right. Now we want to use properties of logarithms to expand the expressions into the sum or difference of logarithms. We want to simplify as much as possible. We don't want any exponents or radicals in our answers. Okay, so let's look at this first one. We have log base 5 of 25y squared. That argument is 25 times y squared. So we can use that product property to split it up. So that's going to give us log base 5 of 25 plus log base 5 of y squared. All right, so if we look at that 25, we can evaluate that. We set it equal to y, and then we convert to exponential form. We can see that we need 5 squared to get 25. So we can simplify this to 2, and then we have log base 5 of y squared. We can bring that 2 out front with a power property to give us 2 log base 5 of y. And that's going to be as simplified as we can get. Natural log of e divided by a to the 5th times b. So with these, I would always start with the quotient rule. If we have a fraction, always start with the quotient rule. Get rid of that denominator. So that's going to become natural log of e minus natural log of a to the 5th times b. We already discussed this natural log of e. That's one of those identities that just equals 1. Now we have natural log of a to the 5th times b. And we can split that up. But whenever we split it up, we want to be careful to use parentheses. We split it up into natural log of a to the 5th plus natural log of b. Okay. So that natural log a to the 5th, we can bring that 5 out front. And natural log of b, we need to make sure we distribute that negative in there. So we end up with 1 minus 5 natural log of a minus natural log of b. And that's as simplified as we can get. Okay. Now we have natural log of y divided by square root of x. Using the quotient property, we get natural log of y minus natural log of square root of x. It said that we don't want any kind of radicals or exponents. So what is another way to express square root of x? It is x to the 1/2 power. And then we can use that the power property to bring that 1/2 out front. So we'll end up with natural log of y minus 1/2 natural log of x. And that is as simplified as we can get. Last one of these, log of 4x cubed divided by k. So again, use that quotient property first and get rid of that denominator. So we're going to have log of 4x cubed minus log of k. Okay, there's not much we can do with log k, but log 4x cubed, we can use the product property. So we're going to have log of 4 plus log of x cubed and minus log of k. Log of 4, it's one of those, it's not a neat number. It's not easy to do. It's not going to be some nice whole number. And so we would just leave it like that. We don't need to simplify that one anymore. But the log x cubed, we can use that power property and get that 3 out front. So our final answer is going to be log 4 plus 3 log x minus log k. And we can use these same properties to combine logarithms as well. So we want to combine all these into a single logarithm with a coefficient of 1. Simplify as much as possible. It doesn't really matter which order we do it in. So let's just go from left to right. So we have natural log of 15 minus natural log of 5 plus natural log of 2. So to combine those first two, we use the quotient property, and it's going to be natural log of 15 over 5. We can simplify that. 15 divided by 5 is 3. Oh, forgot the 2 over there. Plus natural log of 2. Now we can use that product property to combine those two, and we get natural log of 6. Okay. Now, log of 6 plus log of 5x. So if we want to combine those two, we use the product property. It's going to be log of 6 times 5x, or log of 30x. And then the last one, 2 log base 2 of x plus 3 log base 2 of y minus log base 2 of z. Here, when we're doing these, we want to get that coefficient back into the argument first. We want to use that power property before we combine anything. So let's rewrite this first as log base 2 of x squared plus log base 2 of y cubed minus log base 2 of z. Okay. So now just working from left to right again, we'll combine the log base 2 x squared and log base 2 y cubed to get log base 2 of x squared y cubed. And we still have log base 2 of z. And then finally, we'll use our quotient rule, quotient property. So we'll end up with x squared y cubed over z. So that's our final answer, log base 2 of x squared y cubed divided by z. Now, solving our exponential equations. Let's take a look at these. So our first one, we've got 3 to the x minus 2 equals 9 to the 5x plus 2. So the first step is to get those bases to be equal so we can use the equivalence property. We know that 3 squared equals 9, so let's rewrite it like that. So on one side, we'll have 3 to the x minus 2, and then we're going to have 3 squared raised to the 5x plus 2. We can simplify that left-hand side. It's going to be 2 times 5x plus 2. Make sure to put the rest of those parentheses, so the rest of the exponent in parentheses, so we distribute that 2 throughout the entire exponent. So we get 3 to the x minus 2 equals 3 to the 10x plus 4. Now we've got the same base. So we can set those exponents equal to each other. So we get x minus 2 equals 10x plus 4. If we subtract x from each side, we're going to get negative 2 equals 9x plus 4. If we subtract 4 from each side, we'll get negative 6 equals 9x. Divide each side by 9, we get x equals negative 6/9. And if we want to simplify it a little bit, we can divide by 3 to get x equals negative 2/3. Okay, so now we've got 2 times 2 to the x minus 1 plus 3 equals 93. So the idea here is we want to get this little section here. this 2 to the x minus 1 all by itself. So let's start by subtracting 3 from either side. We're going to get 2 times 2 to the x minus 1 equals 90. Now, if we divide each side by 2, we'll have 2 to the x minus 1 equals 45. So here, this is not an easy one to kind of, we can't change that 45 over into anything nice base, right? So what can we do here? Here, what we can do is we can take the logarithm of each side. It doesn't matter if we do a log base 10 or log base e. The fact is that we want to get that x minus 1 exponent not in the exponent. And so let's just take natural log. We take natural log of each side. Now we have natural log of 2 to the x minus 1 equals natural log of 45. And so now we can use that power property to get that x minus 1 out front. So we can change this to x minus 1 times natural log of 2 equals natural log of 45. Now we can divide each side by natural log of 2. And add 1 to each side. And if we plug that into a calculator, we get 6.492. Okay. Now, we've got 4 e to the 2x minus 5 equals 3. So again, let's get that e to the 2x all by itself. So we'll start by adding 5 to either side. So we'll have 4e to the 2x equals 8. Now if we divide each side by 4, we'll get e to the 2x equals 2. And now we're at that same kind of thing, right? We'll never get that e and the 2 to have the same base. So the best thing to do is take the logarithm of each side. If we have a base e, we absolutely want to take the natural log. So again, we'll take natural log of e to the 2x equals, equals, we need to do it to both sides, natural log of 2. Okay, this part right here, this is another one of those properties. If we have a base e with a argument base e raised to some power, that's going to be equal to just that power. Again, we don't have to remember that property. We could use that power property to bring down that 2x, like so. And this natural log of e just goes to 1. So we're left with 2x equals natural log of 2. Divide each side by 2. And calculate it, and we get 0.347. Next one, 5 to the 2x equals 10. So here we could, we want to do that same thing. We want to take the logarithm of both sides. We could do a natural log, but here we've got this 10. And so if we did a log base 10, then that would make that right side of the calculation a little easier. So let's do a log base 10. So if we just take log 5 to the 2x equals log of 10. Now that log of 10, since it has a base 10, is just equal to 1. And on the left side, we can use that power property to bring that exponent out front. So we get 2x log 5. Now, that 2 and that log 5 are just another number. Those are both just numbers, right? So if we kind of rewrote it as 2 log 5x equals 1, then we can divide both sides by, let me rewrite that a little different. I'm sorry. Let's say if we have 2 log 5 of x equals 1, then we can divide each side by 2 log of 5. And so x is just going to equal 1 over 2 log 5. Or if we calculate it, we get 0.715. From this step right here, we could just divide by log 5 and then divide by 2. I just combined it into one step. Either way you want to do it is fine. Okay. So now we have 50 minus 3 times 0.78 to the x minus 10 equals 21. So again, we want to get this kind of exponential part right here all by itself. So the first thing we would do is subtract 50 from either side. So we will get minus 3 times 0.78 to the x minus 10 equals 29. If we divide each side by negative 3, we still have 0.78 to the x minus 10 equals negative 29 over 3. Okay, so now this is another time we'll never get those two bases to be the same, so we should take the log of each side. Again, it doesn't matter if you do log base 10, log base e, or natural log, or any base. It really doesn't matter, as long as you do the same on both sides. So let's just do natural log. So we'll do natural log of 0.78 to the x minus 10 equals natural log of negative 29 over 3. Oh, I made a mistake here. So back here, this 29 should have been a negative 29. 21 minus 50 would be negative. So when we take negative 29 and divide by negative 3, we should have a positive 29 over 3. So then we're just left with natural log of 29 over 3. All right. Now we can use the product property to bring that x minus 10 out front. And we can divide each side by natural log of 0.78. So we're left with x minus 10 is natural log of 29 over 3 divided by natural log of 0.78. And if we add 10 to each side, we end up with 0.905. Okay. Last example. Right. We've got 5 times 1.3 to the x plus 4 equals 104. So we want that 1.3 to the x all by itself. So we'll start by subtracting 4 from either side. That gives us 5 times 1.3 to the x equals 100. We divide each side by 5. 1.3 to the x equals 20. And here again, we'll never get those two bases to be the same. So we'll take a natural log or log of each side. So natural log of 1.3 to the x equals natural log of 20. Use that power property, get that x out front. And then divide each side by natural log of 1.3. We'll just put this into our calculator. and we get x is 11.411. All right, let's solve some logarithmic equations. We want to get exact answers. So the idea here is we want to get into a form where we can convert it to an exponential. So for this first one here, 2 log base 5 of 5x equals 4. We need to get rid of that coefficient of 2. So let's divide each side by 2. That gives us log base 5 of 5x equals 4. So now we can, oops, that is not right. 4 divided by 2 is 2. Okay, that looks better. So now we can convert this to an exponential. That means 5 squared equals 5x. What is 5 squared? That's 25. And divide each side by 5. We get 5. And if you're ever unsure of your answer, take this 5 and plug it back in. So calculate 2 log base 5 of 5 times 5. Now, you might not be able to do that with a calculator, but we can convert it to a different base and figure that out. That's one way to do it. Okay. Let's look at 5 log x plus 3 equals 10. So again, we want to get like a log all by itself on that left side. So let's start by subtracting each side by 3. We'll get 5 log x equals 7. Divide each side by 5, and we get log x equals 7 over 5. Okay, so convert it to an exponential. A log with no visible base shows it means it's going to be a base 10. So we have 10 to the 7/5 power equals x, and we can just plug that straight into our calculator, and we get something like 25.119. Okay. Next one, 8 log x equals 2. So again, get that log x all by itself. Divide each side by 8. So log x equals 2 over 8, or log x equals 1/4. Convert to exponential. 10 to the 1/4 equals x. Now we can plug this into our calculator, and we get x equals 1.778. Now we've got natural log of 2x equals 2. So we already have that log on the left side all by itself, so we can immediately convert to exponential form. Natural log has a base of e, so e to the 2 equals 2x. We divide each side by 2, we're going to get e squared over 2. And that we can just put straight into our calculator. And we get 3.695. 2 log 3x plus 5 equals 15. So again, we want to get that log 3x all by itself. Start by subtracting 5. So we get 2 log of 3x equals 10. Divide each side by 2. Log of 3x equals 5. Now convert to exponential. That means 10 to the 5th equals 3x. Or if we divide each side by 3, 10 to the 5th divided by 3. And if we plug that into our calculator, we get 33,333.333. Bunch of threes. All right, and last one of these. 5 log base 2 of x equals 25. So we want to get that log base 2 of x by itself. So log base 2 of x, we'll divide each side by 5. So 25 divided by 5 is going to be 5. And then we convert to exponential. So 2 to the 5th equals x, or x equals 32. All right. A car tire has a slow leak, and the tire pressure in pounds per square inch, excuse me, after t minutes is given by P of t equals 32 times e to the negative 0.2 t. Let's find the pressure after 1 minute. So that's when t equals 1. We want to evaluate P of 1. So that'll be 32 times e to the negative 0.2 times 1. When we put that into a calculator, we're going to get 26.20. Okay. After how many minutes is the pressure 15 pounds per square inch? So here we know P of t. This is our P of t. We want to know what is t when P of t equals 15. So we will say for our 32 e to the negative 0.2 t equal to 15. So let's solve for t. Divide each side by 32. E to the negative 0.2 t equals 15 over 32. Now, the best thing to do here is take the natural log of each side because we have that base e. We have that base e, it's just going to kind of cancel out that natural log on the e, and we'll just be left with that negative 0.2 t. So that natural log and the e kind of cancel out. We're just left with negative 0.2 t equals natural log of 15 over 32. We can divide each side by negative 0.2. So we get natural log of 15 over 32 divided by negative 0.2. When we put that into the calculator, we get 3.794. Okay. Suppose Mr. Mendoza starts a rock band, log rhythm, and the total number of fans can be modeled by the function y equals 1000 e to the 0.25x, where x represents the number of months since he started the band. Use the function to estimate the total number of fans after 12 months, round to the nearest and the whole number. So we just want to evaluate the function at 12. So what is, let's say if this function is called f of x, then what is f of 12? It's going to be 1000 e to the 0.25 12. And once we calculate that, we get 20,085.53. Okay. How many months does it take until the band reaches a total of 50,000 fans? This is our f of x. When f of x equals 50,000, what is x? So we'll take 1000 e to the 0.25x equals 50,000. Okay, we can divide each side by 1,000, and we get e to the 0.25x equals 50. So again, take the natural log of each side. Natural log of e to the 0.25x equals natural log of 50. That natural log and the e kind of just cancel each other out. And we're left with 0.25x equals natural log of 50. Divide each side by 0.25. And calculate to get a value of 15.648. Okay. Suppose Sally borrows $3,000. She does not need to make any payments, so the future amount is $3,750 after 3 years. If the interest is based on continuous compounding, find the approximate value of the rate R. Okay, so we know that she's going to end with 3,750. We know she started with 3,000, and we know it was in the account for 3 years. So here we know everything but R. So let's plug in what we know and solve for R. So we have 3750 equals 3000 e to the 3r. Okay, so divide each side by 3000. I'm going to go ahead and flip the sides around too. So we have our variable on the left side. That's going to give us 3750 divided by 3000. Again, we have that base e. So take the natural log of each side. So natural log of e to the 3r is natural log of 3750 over 3000. Natural log and the e kind of cancel out. We're left with 3r equals natural log of 3750 over 3000. Divide each side by r. It's going to give us natural log of 3750 over 3000, all divided by 3, or our r is going to be 0.074. So that means a 7.4% interest rate. Harry invested $2,500 and the future amount grows to $25,000, compounding continuously at a rate of 7.5%. Find the life of the investment, T. So here we know that our initial investment was $2,500. Our future amount was $25,000, and we had a rate of 0.075. So the only thing we don't know here is how long it was in the account. So let's plug in what we know. We know 25,000 equals 2,500 e to the 0.075 t. Now we want to solve for t. We want to divide each side by 2,500. I'm going to go ahead and flip it around again. So 25,000 divided by 2,500 is 10. Again, we have that base e, so take the natural log of each side. And use that property so that natural log and the e cancel out. So we're left with 0.075t equals natural log of 10. Divide each side by 0.075. And we get t is 30.7. So it took 30 years to grow $2,500 into $25,000. On to systems of equations. So when we have two equations, and we need to solve them graphically, the first thing we want to do is get them in slope-intercept form so they're easy to graph. So if we start with that x plus y equals 4, subtract x from each side, and we get negative x plus 4. So let's plot that. So negative x plus 4. That means we have a y-intercept of 4, and it has a slope of negative 1. So as we go down 1, as we go right 1, we go down 1. And so on. It's just going to keep going down like so. Let's see how straight of a line I can get. Not super straight, but it's okay. Now let's look at our other. We have 2x minus y equals 2. So let's add y to each side and then subtract 2. Okay. So now we are starting, we have an intercept at negative 2, and we're going to be going up. As we go right 1, we'll go up 2. We have a slope of 2. It's going to be something like that. And we see we've got this intersection at the point 2, 2. And that is our answer. Where they intersect is the solution to the system. So that's one way to do it. We can also use the substitution method. So here, what we want to do is we'll take one of the equations and solve for either x or y. We just want to do whatever is the easiest. Here, this x plus 3y equals 5 is going to be our easiest option. So we'll solve for x by subtracting 3y from either side. Now, we'll take this x and plug it in right there. So that'll give us 3 times 5 minus 3y minus 2y equals negative 18. All right, so let's expand that out. 15 minus 9y minus 2y equals negative 18. So that's 15 minus 11y equals negative 18. Or negative y equals, let's see, add or subtract 15 from either side, we'll get negative 33, which gives us, after we divide each side by negative 11, y equals 3. So now we can just take that y equals 3 and plug it into either one of our equations. It doesn't matter. I'm just going to plug it into the first one. So if we take our x plus 3y, but instead y is 3, equal to 5. So x plus 9 equals 5, or x equals negative 4. Oops, sorry about that. So our solution is negative 4, 3. We can also solve systems of equation using the addition method. So the idea here is we want to get either our x coefficients or our y coefficients to have the same but opposite number. So here, we already have a positive 4 and a negative 5 coefficient for y. So since those are opposite, we should start there. So what that means is we want to find what is that least common multiple of 4 and 5. And one of the easiest ways to do that is just what's 4 times 5? That's going to be 20. So we want to get a 20y in our first equation, and we want to minus 20y in our second equation, so that when we add the two equations together, they will cancel out. So the way to do that is we multiply our first equation by 5 and our second equation by 4. Now make sure to do it all the way across. So the first equation is going to give us 55x plus 20y equals negative 25. That second equation becomes 8x minus 20y equals 88. All right, so now we want to add these two equations together. Here, that 20y and negative 20y cancel out to give us 0y. And really, we don't have to even put that there. But let's see, 55x plus 8x is going to be 63x. And then negative 25 plus 88 is 63 also. So we have 63x equals 63, or x equals 1. Okay, so now that we have that x equals 1, we can plug it back into either equation, whichever one I guess is easiest. It doesn't really matter. Let's do in the second one. So we have 2 times 1 minus 5y equals 22. We subtract 2 from either side. We get negative 5y equals 20. Divide by negative 5, and we get y equals 4. So our solution is 1, 4. Okay. Admission prices to a movie are $4 for each child and $7 for each adult. If 75 total tickets were sold for $456, how many children tickets and how many adult tickets were sold? So, first, let's define some variables. Let's let X equal the number of children's tickets. And let's let Y equal the number of adult tickets. Now, we know we're going to need two equations, and we have to use this problem to help solve it. So, first thing we can do is we can look at how many tickets were sold. There was 75 total tickets sold. We know that there were children tickets and adult tickets. So, if we add the number of children tickets to the number of adult tickets, it should be 75. Now, we also know that the $4 for each child and the $7 for each adult, if we add up those prices for each of those, for however many tickets are sold, it's going to be 456. So, if $4 per child ticket plus $7 for adult tickets, it's going to equal a total of 456. So here are our two equations. Good. Now, let's solve them. Okay, so let's do the substitution method. I think that's one of these is usually a little easier. So we'll use this first equation. So we have x plus y equals 75. So we can say x is 75 minus y. Now we can plug that into our other equation. We have to plug it into the other one. So we'll take 4 times x, which is 75 minus y, plus 7y equals 456. Now, this will be 300 minus 4y plus 7y equals 456. So 300 plus 3y equals 456, or 3y equals 156, or y equals 52. Now, plug that back into either one of our equations, whichever one's easiest. I would go with that first one. So we'd say x plus y, or 52, equals 75, or x equals 23. So our answer is 2352. That means 23 children's tickets were sold and 52 adult tickets were sold. Okay. The total number of global data breaches involving identity theft in 2014 and 2015 was 1,739. There were 95 fewer incidences in 2015 than in 2014. How many data breaches were there in each year? So, first, again, let's define some variables. Let's let X be the number of incidents in 2014. And Y is the number of incidents in 2015. Okay. So here we need to figure out what are our functions, what are our equations that we can use. So we know that the total number was 1,739. So however many there were in 2014 plus however many there were in 2015 is going to be 1,739. And then there were 95 fewer in 2015 than in 2014. So that means that our 2015, we take our 2014 minus 95. So there were fewer in 2015 than 2014. So we take our 2014 and subtract how many fewer there were. So now we have two equations. And we've already got one set up where it's equal to y. So we should probably use the substitution method. So let's plug in y equals x minus 95 into our first equation. So x plus x minus 95 equals 1739, or 2x minus 95 equals 1739. Add 95 to either side. We get 2x equals 1834. Divide each side by 2, and we get 917. Now, we plug this back in to either of our equations. Let's just do the second one. So we have y equals x, or 917, minus 95. Y equals 822. So our answer is 917 and 822. So there were 917 incidents in 2014 and 822 in 2015.